My name is Mike. I am a first-year PhD student in stats, working with Pascal and another prof named Muju from statistics. And I'm also one of the TAs for this course. I will be presenting for the first part of this lecture. It's not going to really be so much of a lecture as a tutorial. It won't be very long. I'm going to take about 20 minutes, and I'll be discussing working in OpenAI environments and designing your own environment and the challenges that that can pose. After I'm finished, we will take a 5-minute break just to switch presenters. And then my colleague Tim, who's another TA for this class, is going to be giving a brief introduction on writing deep reinforcement learning agents in TensorFlow and an example of deep Q networks for cart-pole V0. Okay. So a brief introduction about OpenAI. If some of you don't know about it, it's probably one of the most eminent names for reinforcement learning. Its contributions are, at least in my mind, on par with those of Google DeepMind. But where Google DeepMind employs like 6,000 researchers, OpenAI has about 60 people. But they employ a lot of really recognizable researchers, and they've come out with a lot of very interesting research in the last few years. OpenAI is interesting. Their focus isn't so much reinforcement learning. It's a more broad artificial general intelligence, which I can't remember if Pascal mentioned, but pretty much everything we talk about in this course is narrow artificial intelligence, meaning that we're just training an agent to perform a particular task and to do that really well. But AGI is about building an agent that can perform any task just like a human can, to be good at multiple things and to be able to extend its experience from one domain to another. And their stated goal is about promoting research towards safe artificial general intelligence, which I thought was interesting, so that they're focused on making sure that when AGI eventually comes out, it's going to be a benefit to humanity and not some sort of Terminator situation. And they are not for profit, so they're just funded by donations from individuals and companies. So GYM is a set of environments for reinforcement learning tasks, and it's become pretty much the standard benchmark for all research in reinforcement learning. The standard formula for a paper these days is to pretty much theoretically develop your algorithm that you're proposing, and then to run it on some or all of the GYM environments to show that it either outperforms other people's algorithms or maybe that it learns faster than those algorithms, because that's a big concern. And the ones that we're seeing on the screen here, so the cart pole and mountain car and pendulum, those are all from classic AI papers, so I guess they're from like the late 90s and 2000s. And those are all tasks that were proposed and solved a long time ago. So they've gradually extended the GYM environment to include a lot of other tasks as well, like Box 2D environments and Mujoko, which I guess we won't see any examples of today, but they're a little more complicated because as the algorithms progress, it's becoming too easy to solve the existing problems, so they're extending it to more complicated ones. And some recent extensions that they've made are the robotics environments, which this was my lovely GIF I mentioned that's not playing now. But they have, for example, this hand which is manipulating a ball. There's another one where it's trying to manipulate sort of a pencil. And those tasks are about getting the object in the hand to a particular position and orientation in space. And they're really high dimensional because the hand that they have here has a lot of degrees of freedom, and they're all continuous control tasks. So what they said when they released this environment was that Mujoko, which was sort of, I guess, their next most recent release of tasks, is now easily solvable with algorithms like proximal policy optimization. And so they wanted to release a harder set of continuous control tasks to keep people engaged and sort of stay relevant with the research. And the other set of environments that they recently released, or at least a contest that they've recently started, and it's on right now, actually, it ends in early June, is called the Retro Contest. And what that aims to address is the idea that only in reinforcement learning of all of the other machine learning domains do we test and train on the same data. So for reinforcement learning, we just run a fairly, well, relatively small deep learning model on an environment for a lot of episodes until it's good. And we report that the performance it eventually achieves. And in image recognition, that would be equivalent to running a computer vision model on ImageNet for a really long time until you could get very good classification on that. And not having a test set, just reporting your training set accuracy. So what they did was they have these Sonic the Hedgehog environments for Sega that they've released. And those environments are all accessible to everyone. What they want people to do is to train an agent on those that learns how to perform in new levels. So what they have is some secret custom levels that they've designed that no one has a chance to train on. You're supposed to train your reinforcement learning on the existing levels and then send the trained model to them. They take that trained model and evaluate it on the new levels that the reinforcement learning agent has never seen and report back to you on how it's scored. So what they want is for the reinforcement learning agent to be able to extend the experience it got in previous levels into a new level it hasn't seen before. And that's actually like a very real challenge, is that the reinforcement learning agents aren't particularly good at extending to a similar but essentially different level of the same game. So the next part of the presentation that I'm going to talk about is probably what's most relevant to you guys. This will be helpful for the first assignment. I don't know, did Pascal release what that's going to be yet? No, so I won't tell you then. But at least it'll be relevant to you guys. And I'm just going to show you some really basic code for how you interact with a gym environment. This is very basic stuff, and I'm going to go through it at a pretty low level, just so everyone's on the same page. And the code that I'm going to show you is applicable across all gym environments because they've standardized how you do this. Okay, so the basic code for interacting with these, no, that's the screen. Lovely. For interacting with these environments, you import gym, which is a Python module. And pretty much the first step that you want to go through is declaring which task you're going to be working in. So it's this gym.make function, and you just feed it the identifier of which environment you want to work with. So for here, I've said it's cartpole v0, and there's different versions of these. So cartpole v0 is going to give us a particular version of the cartpole task. Okay. And pretty much, I've removed all parts of this code that have to do with actually training your agent. So this is just about how you would run through episodes with a reinforcement learning agent. But what you tend to have is a nested for loop where the outer for loop is going to handle the episodes that you want to go through, so how many episodes we want to perform. And the inner for loop is going to handle stepping through time in those episodes. At the start of each of these episodes, you have this env.reset function. And that's basically going to take the environment back to the starting point of an episode, and it returns to you what the initial state of that game is, which can be random or deterministic. And then for each time step of the episode, we're going to want to predict what action we should take at this time step, which is going to come from our agent, taking the current state in as input and predicting an action for us. And then the next most important thing is the env.step function, which is we feed it the action that we've predicted. It has an internal log of all of the variables relevant to where the environment is right now. It's going to take the action that we've given it, as well as its knowledge of what the current state is, and return to us what the new state is going to be based on its internal transition function, and the reward that we would earn for taking a certain action in a certain state and then moving to a different state. And finally, this done variable, which I'm not sure whether Pascal's talked about it, but that's going to be about whether the episode should terminate at that step. So for example, the agent could be finishing, or it could have crashed into something, and we'd say the episode should end here. And the final step for this is then to just say our current state is now what we previously called the next state, and we've moved one step forward in time. Is that clear? I think it's pretty clear, yeah. Quite basic, right? All right. And then the last thing that I'm going to talk about before we take a quick break is about building your own environment. And I wanted to mention this when I had the chance. It's something I've had a little bit of experience with, and I think it's of more practical importance than just beating a gym environment, because the gym environments are really useful for having comparable results on the different algorithms in research. But realistically, what you actually want reinforcement learning for is to come up with automated solutions to different tasks that don't already have a gym environment for them. Those have all been solved. So if you wanted to teach a robotic arm how to do something, you would most likely want to make your own environment that rewards it for doing the thing that you want it to do, and so that you can make an agent that is actually able to perform that. So building your own environment is actually much more important in the real world than operating inside a gym environment. And so I begin by saying it's really not that difficult to build your own environment. I've done it, and I basically can't code at all. So it should be possible for all of you. And all it involves is just a Python class with methods for pretty much exactly what I explained in the code before. So initializing your environment, a step function, reset for going back to the start of an episode, and then a rendering function, which is useful for understanding what your agent is learning inside of that environment, and also evaluating whether the transition dynamics that you've coded in seem visually realistic. And most of the heavy lifting for this task is done by existing physics engines like Box2D and MuJoCo. I don't have any experience with MuJoCo, but for Box2D, it handles all of the physical simulations. So for example, what should happen if two objects inside your environment collide? How should they react to each other? It handles all of that calculation. And it also has operations for rendering as well, so it makes it pretty easy for you. And yes, this was another one of my gifts. This is an example of a project that I've been working on with Pascal. It's a collaboration we have with Ford. And what Ford's interested in is deploying reinforcement learning algorithms for teaching a car how to park itself. So how this is typically done now, they tell us, is actually pretty much through rules-based systems. And that really limits the number of scenarios that are that can be handled by that parking program. So they pretty much just have like something for parallel parking and something for maybe pulling forward into a spot. And the number of different places you can use that is very limited. So you have to kind of be able to see the spot where you are, and then you just have to tell it, okay, go, and it'll handle getting in there. But as far as searching around a parking lot and finding a spot for you, it can't do that. So the idea of being able to go to a mall and get out at the front door and say, okay, go park yourself while I'm shopping, that's definitely not possible today. And the challenge here for the reinforcement learning agents is that they have to be able to react to a new parking situation where, just like those Sonic the Hedgehog levels, we've trained it on however many different configurations of a parking lot you can imagine, but there's always going to be a parking lot that is different in some way. And the reinforcement learning agent is going to have to be able to react to those predictably and safely. So this is really basic, the most basic situation that there is for parking. It's an empty parking lot with one parking spot, and it's perpendicular parking. And that's something we're going to be extending. I did have it as a GIF, like I said, showing how the agent learns to navigate towards the spot and pull in consistently. And a major challenge that you don't anticipate when you start to build environments is that it's actually very difficult to create a good reward function. When you're working with gym environments, that isn't immediately obvious to you because they provide you with a reward function that's already very good, actually. And they've spent actually a fair bit of time in defining those reward functions so that it's easy enough for the agent to learn. And the issue here is that reinforcement learning agents can learn to exploit gaps in our logic as programmers. So I can provide all sorts of reward signals to an agent that I think are going to encourage behavior that will be helpful to completing the task I want it to. So what I mean is that I can give this car a reward for being pointed in the direction of the spot that I want it to go to. And I think that's going to encourage it to generally be pointing at the spot, and that'll be helpful. But something that can happen is it might just turn and then point at it and stop, and just be earning that reward endlessly, and just go on accumulating those rewards forever. So even though I think it encourages behavior that should be helpful for getting the car to park itself, which is, in this case, pointing at the spot, the strategy that maximizes the expected discounted sum of rewards, which is always the end goal for these, might be something that we don't expect and which isn't actually very helpful to the task we want it to complete. And this Ng et al. Paper from 1999, that's Andrew Ng, that you guys may have heard of. It goes through some interesting examples about this. Another one about an agent that's supposed to be riding a bicycle from point A to point B. And the rewards that they gave it ended up making it just go in circles, because that was actually a more valuable strategy for it than just going to the destination that they wanted it to go to. And this is my last slide. So it turns out, really, if you have a goal in mind that you want your agent to perform, a theoretically correct way that sort of will consistently work for you and that avoids all of that trouble is to just give it a reward of 1 if it does exactly the thing you want it to do, and 0 otherwise. And then eventually, with the Q function or value function or whatever you're using to do your reinforcement learning, that will propagate back to other states based on the probability model that it learns of your environment. And it'll eventually learn to do the right thing. But that's what's called a sparse reward. And in practice, it's very difficult to learn because, for one thing, it takes a long time for that reward of 1 to propagate back to other states to give it a preference of what to do. And also, for it to ever learn anything, it has to succeed in doing the thing you want it to do at least once before it receives any signal about what actions are preferable or not. So if it's never succeeded, it will only have ever gotten 0 rewards, and it won't have any reason to prefer one action over another. And the area of research that tries to deal with this is called reward shaping, which is basically, we have some sparse reward signal like this 1 and 0 setup, and we want to make that more dense, essentially, where we have a reward signal at every step that gives the agent a better idea of whether it's doing the right thing or not. But the key thing is that that can't change what the optimal policy is. So in the example where I was talking about my car learning to park itself, if I add that reward about it getting some reward for pointing at the spot, the optimal policy changes from going and putting itself in the spot to just stopping and pointing at the spot. So I don't want my optimal policy to change when I add that shaping function to my reward. And that's the real challenge that they aim to deal with. So this Ng et al. Paper just had an interesting mathematical analysis where they showed, this is definitely not testable or anything, but I thought it was interesting, where they showed that if you have a shaping function that has the form shown here, then that will preserve the optimal policy across both environments. And that's basically it. It was just an interesting result. And I guess if you guys have any questions, I can take them now, or I will be hanging around for the 5 minutes and the class afterwards. So if you guys want to come up, that's fine. Thank you.
Sorry, can you explain more about the last equation?
Yes. So what they showed was, with math, that this f function is essentially, we have a reward signal, which we can call, I'll turn the lights on. We can have a reward signal, which we call R. And R basically maps the state actions, state triples to the real line. So whenever I am in a certain state and take a certain action and transition to a different state, I'm going to receive a reward of R. But what we want to do is to add some extra signal to that, F, where F also maps that triple to the real line. And we want to add some extra signal to the reward that we receive at each step. But it has to have the form that the discounted value, or the value that the add has to be somehow proportional to some function phi, which is just a real function, which takes as value the state. And it should always be phi at the next state discounted by one step minus phi at this state. And they don't get any more specific than that. So it's not actually practical, this result, for saying how should I actually shape my rewards. But they do go through some other examples of functions which take this form, and they just showed mathematically that it doesn't change. It preserves what the optimal policy is when our reward is now R plus F, will also be the optimal policy when our reward was just R.
Is that phi the is the phi some expression according to the reward?
No, so the phi is just, we want to add this to our reward, and this phi is just some function that we have to choose, right? So if we choose a function phi that satisfies this, if f is proportional to this relationship, then it will preserve the optimal policy. But phi is something you have to choose, which you think will help improve the learning.
Does that mean whichever action you choose takes long doesn't will not matter, right? Because here it doesn't allow A.
Yeah, I think so. A impacts your probability of transitioning to a different state. And so this should make a difference on which A you prefer. But honestly, I'm not sure quite whether it works that way in practice, where everyone would be doing it.